So we can start our work in progress presentation. The first one is from University of Rochester, Sreepathi.
Hello, everybody. Hopefully, all of you can hear me and you
Yes.
can see my slides. And let me start my slideshow. All good?
Yes, please go ahead.
Awesome. Thank you. So thank you for giving me an opportunity to talk about our work in progress, which is called Ptx Vm. It's about translating PTX to C. My name is Sreepathi Pai. I'm an assistant professor at the University of Rochester. This work that I'm going to be presenting today is actually joint work with my students, obviously. So to give you a reminder, to those of you who do not know, what is PTX? PTX is a virtual ISA. It's used by NVIDIA's GPUs. And the idea behind PTX was to separate the hardware ISA from the changes in the hardware ISA from existing programs. So it was essentially to enable forward compatibility. And the general idea was, as you can see in this figure, if you write a CUDA program, you will get, PTX output. And if it runs on a GPU that is new and that was not available when the program was written, the CUDA runtime will translate the PTX into SAS, which is the binary ISA that the GPU understands and execute the program hence. It was also their intention to let third-party compilers generate PTX. So PTX was a long-lived stable target. So for example, GPU-CC or more recently Clang supports compiling CUDA code into PTX, which can then be compiled into the binary form by NVIDIA's compilers. By the way, feel free to interrupt me if you have any questions on any slides, but I can also take questions at the end. So hopefully everybody's clear on what PTX is. So let me explain to you what Ptx Vm is. So Ptx Vm is essentially a translator at this point in time. And in this slide, I show you two figures. So the figure on my left is PTX. So PTX is, as you would expect, a virtual ISA. So it is something like assembly language. And what you see over here is a function taken from PolyBench, which is convolution 2D. And you see its code over here using, for example, virtual registers and so on and so forth. What Ptx Vm does is it translates that code into C, plain C. Well, it's not plain C, it's C11. So what you see over here is a translation of this PTX code into C. You see the functions being mapped to C functions. You see the registers being mapped to C variables. And then you see each of these instructions being translated into function calls. And this, at a very high level, is what Ptx Vm does. It's not an interpreter. It's translating from PTX to C. So how do you use Ptx Vm? So the first thing you do is you will mostly compile your CUDA programs as normal, except that you must use the dynamic CUDA runtime and not the static CUDA runtime. And you must also embed the PTX files in the binary. This can be done easily. We also support separate compilation, which is something that's available since CUDA 5. And to make all of this easy, we provide a convenience wrapper called NVCC wrapper, which will intercept NVCC invocations, and it will kind of rewrite the NVCC command line so that you can do all of these things without changing your make files and all that sort of stuff. Once you have a binary, you will call the translator, which is called PTXVM make module on the binary. And this translator will extract the PTX files from the binary, no source code required. and it will compile all of them after translating them into a shared object file. Once you have that file, the next step is to actually run the binary, and for that we provide a command called PTXVM run. And you see it over here, PTXVM run you just call the ordinary binary, prefixing it with PTXVM run. And what PTXVM run does is it, like, in most tools that simulate CUDA programs, it will intercept the CUDA runtime calls, and it will, instead of running them on the GPU, it will actually run the translated versions of the kernels on the CPU. So no GPU is required to run these programs now. So the process just adds on to whatever existing method for compilation you have and doesn't require any major changes. So I would like to give you a very quick status of PTXVM. So PTXVM right now has been tested on and can actually run all of Rodinia 3.1, all of PolyBench. It can run all of CUB 1.8's tests and pass them. I think it can run the newer versions of CUB as well. We just haven't tested it. It can run ModernGPU 1.1, which, although the library has been abandoned for some time, is still used by many high-performance CUDA programs. One curious thing about ModernGPU is that it internally uses CUDA's random generation library, cuRAND. And if you link it with the static version of the library, we have no problems running cuRAND too. We can also support running dynamic libraries from CUDA, but we haven't done the engineering work required, but it's not hard. It can run the IrGL graph benchmarks, which is approximately Lone Star GPU, but Lone Star GPU only contains, like the fastest versions, whereas IrGL graph, there are many, many more, and it can run all of them. We've got some really nice support for all the weird barrier synchronization tricks that CUDA DMA supports. We can run examples from CUDA Parallel for All blog, although we haven't done an exhaustive test. We just picked random interesting examples from there and tried them out. But basically, at this point, PTXVM is pretty mature. We are just, going through the list of programs you would like to see supported. And at this point, if a CUDA program has a test suite, we can easily try to support it. And if there's a particular program that you're interested in, you should let us know by email so that we can see if PTXVM needs additional support for it. So at this point, some of you may be curious as to why we are doing PTXVM. What's new in PTXVM compared to the existing tools for running PTX on CPUs. One of the things that's different from PTXVM and those tools is it's not an interpreter, it is a translator. And but that's not a big difference. The big difference is that PTXVM is probably the first implementation of PTX that models independent thread scheduling. This is a new execution model introduced somewhere in PTX 6 for the Volta GPUs. And the idea there is that each thread has its own program counter. There is no guarantee of lockstep execution and no divergent stack. And indeed, we don't support any of these, lockstep execution or divergent stack. We found some interesting things by modeling existing programs using independent thread scheduling. So theoretically, we have shown that it is probably not possible to build a GPU without lockstep execution. So all hardware GPUs will continue to have lockstep execution because there are some instructions that just don't work without lockstep execution. But in practice, what we can also show using independent thread scheduling is you can find all the deadlocks that happen when you are porting these warp synchronous codes to newer GPUs like the Volta. If you were trying to do this using the hardware, you would first have to get rid of all the deprecated instructions and then find the deadlocks, and then manually locate where the deadlocks are. but using PTXVM, you just run them as is, and it'll find all the deadlocks for you. It won't do that automatically. It'll just deadlock, and then you can use a debugger to find out where the deadlock is. We've also found many data races that don't show up because the programs were written using the assumption of lockstep execution, including data races in PolyBench. But I think the biggest change from existing systems is that PTXVM programs are C programs. And C programs have a very vast ecosystem of tools, sanitizers, fuzzers, tracing, symbolic execution. And now you can run all of them on PTX programs, which is something like the CUDA ecosystem does not really support many of these things. So that's what we are interested in. But one of the key parts about PTXVM that I wanted to tell you about is its architecture, which is that from day one, we've built it to be reusable and modular, so that all of its pieces are very loosely coupled, and you can pick and choose its pieces to use for your research tasks as well. So for example, some of these pieces are formal specifications of the grammar and instruction semantics, and I will show you in the slides what these look like and how they are very independent and how you can use them in your own programs. We've got a very high coverage parser from that grammar. We've got a very high quality test suite that has already found bugs in many programs. We have a translator, which is the thing that I showed you. We have a skeleton runtime for the CUDA runtime library, whose interpositioning library is automatically generated from the headers, the CUDA runtime headers. We've also written a library to manipulate CUDA binaries, the fat binaries that exist, so that you don't need something like CUOB to dump anymore. You can just use these tools to programmatically manipulate CUDA binaries. So I'll talk about a few of them in the slides to come. But given the restrictions of time, I cannot talk about all of them. I'll be happy to talk about them via email or offline. So let me begin with what we have in the PTX grammar. So this grammar that you see in this figure over here is extended Backus-Naur form using a standard syntax, the W3EBMF format. It is complete 6.5 grammar and can parse nearly all PTX programs. Right now, we don't support debug sections yet, but we are planning to add that before releasing. One of the interesting things about this grammar is that it does not just encode the syntax, which is what you see over here, but it also includes metadata, like what the types of each argument are. Okay, so for example, BFE has an out and an in of a particular type, but the argument B is of the U32 type and so on. But it also includes a schema for generating test cases for BFE. So, and this is the schema, which is a simple schema for BFE. It's just that call the instruction, and that's the test for this particular instruction. And I'll show you what that leads to next. So this whole parser is available as a Python package, and you can, it's not released yet, but it will be available as a Python package that you can use directly. We also have put in a lot of effort into generating a test suite from that grammar. So we have unit tests for every PTX instructions. These are CUDA programs that are automatically generated from each grammar rule. We have more than 60,000 tests, so I think around 63,000 right now. You can see they're organized by instruction, and you can use them to validate any PTX implementation, not just our system. This test suite has already found bugs in multiple versions of the CUDA compiler, and obviously also in GPGPU sim, which you can read about in our ISPAS 2020 poster. A key part of PTX translation is this knowledge of the instruction set semantics, In this figure, I show you what these instruction set semantics look like. They're just C functions that map one-to-one to a PTX instructions. These are automatically generated from a high-level Python DSL. We've got ALU instructions. We've got elementary functions, sine, cos, that are a bit accurate with what the GPU does. And this is released and available on GitHub. Still have to do floating point 16-bit support, but everything else is there. We have control flow support, except indirect jumps, and we support the ABI, so printf and assert statements work. All the synchronization stuff works, textures, partial support. We don't plan to support surface instructions. Let me know if you need them. And we have some other stuff still to do, warp level matrix multiply, video, and so on. So this is built as a library that you can just directly use in whatever you're writing, even if you're writing an interpreter. There is a translator. Obviously, I showed you one example of a translator that was a direct translation before, but that's limited to simple CUDA programs without barriers of warp synchronization. We also have a more sophisticated translator which emulates the PTX programs, as you can see over here, using program counters. And that's because C does not support parallel programming as a first-class construct. Right now, all PTX programs run as a single thread, even on the CPU, but we're planning to make it multi-threaded. There are some challenges that we probably will not solve. To be very faithful to run a PTX program, you need to know how the linker and the loader works, and there are no specifications that NVIDIA provides for this. Also, the CUDA runtime API is just too large. We don't plan to re-implement it, so that's another issue that you will encounter with this. So we hope to release this sometime in summer 2022. If you'd like to have some benchmarks supported, you should let me know by email. Thank you. I can take a few questions.
Thank you so much for sharing your work. Are there any questions from audience? Again, Sreepathi.
Okay, I guess not. Thank you very much. Bye.